Yes, hello everyone. We are Team Pikachu. I'm Jiang, and our team member includes Yulun, Rishi, and Jiaoyang. Today our topic will be scaling lifelong map F to more realistic settings, research challenges, and opportunities. So lifelong map F is basically a map F plus continuous task assignment, and we see wide applications in autonomous vehicles or the virtual games. Yeah, and as a participant, we see a lot of challenging instances in these competitions. And I think Professor Daniel has already introduced. This is the 10,000 agents in a very large sortation map. And well, actually, this scenario is realistic because it's a report 2 years ago from Amazon Robotics. They have already deployed 4,000 agents. So 10,000 agents is no longer a big number. And another instance impressed me a lot is this very dense case, which have 98% density. And we can also find a real application here, which is the auto parking lot. So I would say that this challenging instance was studied in this competition. And since our team wins several checks, I believe you must be very interested in what kind of algorithm we used in this competition. And I will introduce them next. So the very first challenge I believe everyone encountered in this competition is the limited planning time. So we are only given 1 second for each step, but we have 10,000 agents at the most. And as a comparison, in general literature, uh, researchers generally experiment with 1 to 5 minutes, and the number of agents is usually smaller than 1,000 agents. So the first idea we apply is the windowed planning, and it helps us to decompose the lifelong map F problem into a series much smaller windowed map F, so we can handle it in 1 second. And in the window, we try to use the map F algorithm to avoid collisions, and this is we computed the actual costs of these agents. But beyond the window, we just ignore the collisions between agents, and we use their shortest path to the goal location as the estimation. And then during the search, the overall objective would be the sum of these two. Yeah, but if we use windowed planning plus some state-of-the-art suboptimal algorithm like ECBS or PBS, unfortunately, it's not fast enough. According to our experiments, it can only handle at most 400 agents in 1 second. So we actually turn to another very fast algorithm called PIBT. In my understanding, it's a single-step greedy planner which runs in a depth-first search way. And for the case with 10,000 agents, it could return a valid solution within 250 milliseconds. So it's pretty fast. And PIBT is a abbreviation for priority inheritance with backtracking, developed by Dr. Ogruma. So I will briefly introduce this algorithm. Suppose this is the blue circle is our the root of the search tree, and we will sort agents in predefined orders, and then generate the action nodes for each agent at each layer. Suppose the first agent is agent 5, and then we generate its 5 possible actions. And the next question is which action node to expand next. So in PIBT, it uses the heuristic function, which is calculates the shortest path cost to its own goal location. And here the first node has the smallest cost to its goal location. So we will expand it next. But in PIBT there is a so we can continue expand with the predefined order. It's totally a valid DFS algorithm. But in PIBT there is a special mechanism called priority inheritance, which would dynamically adjust the agent order. And suppose the original predefined order is agent 5, 4, 3, and 2. And the first action of agent 5 would move the agent 5 to the original location of agent 2. And if we want to find a valid solution, then agent 2 must be pushed away. So an easy idea is to consider the agent 2 to be the next agent to reasoning. And according to these rules, we can continue to expand this search tree. And in a DFS, then it would return us solution very fast. But it has a relatively low solution quality. In the largest sortation map, it has a throughput of roughly 30. Next, we will introduce the large neighborhood search, which will improve the solution of PIBT to 40. So large neighborhood search is an anytime algorithm. The basic idea is we try to obtain a valid solution fast, then continuously improve the solution within the remaining time. And of course, we start with PIBT. And then in each iteration, this algorithm selects a small subset of agents, what we call neighborhood. And then we use prioritized planning to replan passes for all the agents in this small neighborhood. And if the plan, the subplan is improved, we update this subplan to the overall plan. And luckily, this large neighborhood search algorithm could be easily parallelized. We use a centralized neighborhood selector to propose several neighborhood. And each thread replan for a neighborhood. Then we sequentially update the plan to the global one. Yeah, and this procedure could be done in a synchronized manner, so it could be faster. This is the concurrent work talking about exactly the same idea. And we can see the effect of anytime algorithm and a parallel algorithm. With more time and more threads, we could get better performance. So our solution is finally named windowed parallel PIBT large neighborhood search, which is a combination of several techniques. With the current MapF instance, we use PIBT to generate an initial solution. Then we use parallel large neighborhood search to refine the solution. And then we execute several steps. But if you only use the above method, we would encounter a specific problems in an interesting problem in the lifelong MapF, which is the traffic congestions. And here I show the heat map of the average number of waiting actions happening at each locations. And we can see that so the more red it is, the more congested it is. And we can see the congestion gradually accumulate and become severe and severe. So actually in this competition, we use a method called a guidance graph, or originally called highway in the literature. It's basically we define edge weights at each locations to encourage agents move in certain directions. For example, here for these agents, we define it's at this location we define the cost to move to left to be 1 and the cost to move right to be 10. Then during the planning, these agents would tend to move left. And in the competition, we manually design the map weights for a lot of instances. We generally start with the crisscross weights, which is just encourage agents to move in certain directions, alternatively at each row. And then we run some simulations. If we see there is a congested area, we just try to increase the edge weights, edge costs in this area. So during the planning, agents will use this region less frequently, and the congestion would be reduced. And we do it iteratively, but it's a very tedious process. We later develop an automatic optimization problems, which is covered in one of our team members' paper called guidance graph optimization. And with the guidance graph, well, the congestion is largely reduced and throughput is significantly improved. But in this competition, we observe another cause of the congestion. Specifically in this game map, there are many agents who would go through this small narrow corridor in this region A. So there is a severe congestion. And clearly it's because the number of agents exceeds the capacity of this local region. So we want to reduce the number of agents going through this region. But in this competition, we just use a very ad hoc trick called disabling agents, which simply asks some agents not to go to their goals. And in the implementation, we just randomly select a subset of agents and we set their priorities to the lowest and their goals to their current locations. And so they just move around their current region and would be pushed away if there is some highest priority agents want to go through their locations. And the next question is we need to determine how many number of agents to disable, and we just run a simulation and pick the best one. Yes, and the traffic congestion, yes, by disable agents, the traffic congestion is also reduced, and we almost double the throughput. Yeah, and as a summary, we mainly address these two problems, the limited planning time and the congestion. And in terms of future works, well, of course, the first thing we could improve the above algorithms. For example, recently the hot topic would be combining planning and learning. And another thing is that, for example, the guidance graph, what we use is an offline strategy, and we could probably update it online. Another thing we want to argue is that we could study more realistic models, because in this competition, the task assignment is largely simplified. Yeah. Okay. Yeah, we also organized our code a little bit, but it's basically the same as the one published, make it publicly available by the organizers. Yeah. Finally, is the question and answer section.
Yeah, thanks so much for presenting his work. And question from the audience.
I have a, oh, go ahead.
Hello, thank you very much for your presentation. I loved it. And I have a question about the anytime algorithm, because so I understood that you optimize solutions that you already have. How do you evaluate them? How do you identify, assign a number to say this is better than another one?
We just compare yeah, I mean, we have an objective function here, which is the actual cost plus the estimated cost. So if we update a subplan for a subset of agents, then we just get a new cost for this subset of agents. And the cost for remaining agents are just keep the same. And so we can compare whether we get an improvement.
Okay, thank you. Thank you very much.
So first of all, congratulations. My question was when you do the parallelizing of the LNS, do you does this result in additional conflicts, and how do you address those conflicts?
Yeah, actually, we only address everything in this sequential update part. I mean, at the beginning, this neighborhood might have some overlaps, or maybe initially some neighborhood get improvement, but if another neighborhood, the path of another neighborhood changes, then this improvement might just disappear. So in this plan update part, we need to do it sequentially. So we check for the plan, the first plan, the first subplan plan first, and then we recalculate whether it's a conflict or whether the cost is improved for the second plan. And yeah, so yeah.
Thank you.
So any other questions? I see Dan raise his hand.
Thank you for your presentation. Maybe I missed something, but what's the main algorithm used for dense instances? Can you please just remind us about?
Yeah, I haven't talked about what kind of algorithm we use in the dense case. Actually, so our overall framework is PIBT plus large neighborhood search, but we find that in the dense case, because our cost is an estimation, if you remember. So what's beyond the window is an estimation, and we find that use large neighborhood search actually make the result worse. And so in the very dense case, we actually only use the PIPT part. And of course, we also use the guidance graph. And I've mentioned that we have an automatic optimization guidance graph optimization, and basically we combine these two technologies for this very dense case. But I think we didn't do very well in this case. Yeah.